Hello. Thanks for joining us today. This is the actual first of a 3 series of around color management. So this is a session between Esko, X-Rite, and Pantone. So we're joining today will be myself, Martin Cusack. As you see from the screen here, that I'm the Esko product manager for color. And my colleague and co-presenter here is Mark. Mark, if you'd like to introduce yourself.
Yeah, hi, I'm Mark Gunlock with X-Rite. I'm a solutions architect, and I'll be presenting today all of our color content.
So as we go through the actual sessions, there will be opportunity for you actually to put some questions. You'll probably actually see it on your right-hand side. It may be that as the actual slides go, as Mark goes through the slides, that the next slide or two will be able to actually answer some of these questions, but it could be that we answer the questions as we go through the actual sessions, but if nothing else, we'll do our best to actually answer the questions at the end. If we were to run out of time, then please do keep the questions coming. We will follow up afterwards. It is something that we'll continue to monitor after the event. So please do that. In terms of the actual, this session will be recorded as well. So directly after this, the actual session will be available for people to actually sort of watch again if necessary. So everybody that's actually been registered will get a copy of that. And as I said, it's one of 3. So for the people actually in North America, there will actually be a link after this for the second session, and the people in EMEA, there will be a link sent out tomorrow for that session. So Mark, over to you.
All right, thank you very much. So let's get started. So what we're going to talk about today first is a little bit about human color perception. Then we're going to move into talking about density. It's not really a standard, and we're going to talk about why it fails as a standard. We'll look at color science, how color works. We're going to look at the numbers of color. How do we quantify these colors? How do we put numbers to them so we can manage them? And then a real critical piece is, what is spectral data and why is it so important? So let's go ahead and dig in. So first of all, let's talk about, with human perception of color, how about color memory? I want you all to look at this color, try to memorize it. Got a few seconds here. Okay, you should all have it now. Let's see how good your memory is. We're going to throw out a bunch of examples here, and I would like you to look at these and just try to figure out which one is the correct one, which one matches the patch that I showed you a moment ago. Okay, so there's some wild different ones in here, but take a look. Okay, you all should have something in mind. Just keep in mind what that letter is for the color you got. And this is the one. I'm going to bet that most of you didn't get the right one. Okay, some of you may have gotten lucky and got the right one, but most of your peers didn't if you got it right. So it's really tough to remember colors, even though we just saw that a moment ago. To try to find that again is pretty tough to do. Okay, now picture a bunch of press sheets. You look at a customer's color, and then you look at a press sheet, and you look at another press sheet, and you look at another one. You're going to get confused. You're not going to remember it well. Another thing that happens with human perception is we can get deceived a bit. If you take a look at these colors here, you see these blues. They look distinctly different. You can clearly see the blues on the right. It appears to be a bit lighter than that on the left. It is, they clearly look different until you take away the rest and you realize they are in fact the same. This is simultaneous color contrast, and it's when we put other colors around the colors we're judging, it impacts how we see those colors. Okay, here's another example. Believe it or not, there's not a green and a blue here. These are, in fact, the same color. If we pulled this into Photoshop and looked at the RGB values, they're actually the same color. But because the one on the right is surrounded by a magenta color, and the one on the left has orange in between it, it impacts how we see the color. So it looks like we've got 2 different colors there. There's no way those look the same, but they are. And then here, if you take a look at this one, again, the surrounding colors impact our judgment of the color. If you look at the little chip in the middle of the left side, the front side facing us, the square in the middle, most of us would describe that as yellow. And the one on the top, most of us would describe that as kind of a brownish or maybe a chocolatey color, okay? Well, they look very, very different until you take away the surrounding colors that are impacting our judgment or our perception of that color and realize they're actually the same. So this is really critical. Again, if you're looking at, say, brand colors, logos, and so on, they're surrounded by other colors. It's going to impact how you perceive that color. If I took an instrument and measured those two patches, they'd measure exactly the same, but we perceive them differently, okay? So this is where our ability to view colors and judge colors visually is very limited. You can't remember the color, and you can't even, in this case, see the color near each other and be able to tell the difference, or in fact, tell they're the same. Now let's talk a little bit about density being used as a standard to control your press, okay? So I run into this all the time. You got a press operator and say, hey, I'm going to run my standard densities on this job. I don't need color. I just need density. The ink's the ink, right? Well, so I've got a density standard here for my press operator of 105. Now, this what I'm going to show you here is actual measured stuff, okay? This is real world stuff here, okay? We've got our first sample, measured 106. That should be pretty good, right? We'd take that all day long. If that was our target was 105 and we measured 106, all good, right? But our second sample here is also 106. It's kind of close looking, maybe. And a third one is 97. So I would guess that'd be a little bit lighter, but it doesn't look it. Kind of deceiving, right? So if I look at these colorimetrically, and I've got yellow as my LAB as a standard for my yellow, okay? I've got actual color data targeting this. I will see that my measured results down below, the delta E's, are significantly different. So the one on the left, that one's probably going to pass. The other two, not so much. In fact, when we look at the colors more closely, we can see that the LAB values are significantly different. And when we put the colors up against each other, you can see an even greater difference between them. And now keep in mind, the two on the left were passing under density, and the one on the right, according to density, said it was too light. But in fact, because it's contaminated with other inks, the yellow component measured as too light, but it looks dirtier. And so if we made adjustments of our yellow ink, which in this case is a dirty yellow ink, we would see that 0.97, and we would probably bring up the density on this and make it even worse. Whereas if we look at it colorimetrically, we'd recognize this is not a density issue. This ink is contaminated. It's way off in color, and we need to do a wash up on that unit and replace the ink. Very different behavior based on measuring color instead of density. All right, so let's take a look at some color science. So the way color works is you start out with light, you reflect it off objects, and the objects will absorb some wavelengths of light and reflect others. And the press operator or an instrument or your customer, they're going to see the color based on what reflects off of that product or off of that package. So starting with light as the first part of our color is we can see, if you remember back in school, when we put light through a prism, it would split up the wavelengths of light into the rainbow, okay? Or what sometimes people would call Roy G. Biv, which would be red, orange, yellow, green, blue, indigo, violet. And if you break that into bigger chunks, it's red, green, blue, okay? Shades of red that are from the red through yellow, the green, and then the blue, which is the blue, indigo, violet. That's all of our color of light. That's what's in the light source. Now we got lots of different light sources that we think of as white, okay? Our eyes will adjust for the light that we're under, making it seem white, okay? But it's adjusting for that on the fly. But in fact, if we look at these, they're all very different color. Daylight throughout the day will have different amounts of energy throughout the spectrum. Okay, so here's just 3 examples of what we call daylight spectral distribution curves. And you'll see that Some of these curves show more blue in them, and others show a little bit less blue, depending on where the sun is in relation to the horizon or in the middle of the noonday sky. The color of the sun or daylight is going to be a little bit different. It's going to vary a bit, okay? In our print industry, we've standardized on a specific daylight, which is called D50. And it's a curve very similar to one of these. What's important about that is the amount of energy across the spectrum is fairly even. It's more even than some other lighting conditions at that point. Here is the old incandescent light bulb. And not many people have these in their homes as much anymore. They've moved to other kinds of lighting, but this does still exist out there. And you can see with this lighting, it's got a lot of red energy in it and very little of the blue and indigo and violet energy in it. Okay. Now, when you're under that lighting, you don't see that much of a difference. But if you're, say, outside a house and you look into the house or apartment, you'll see that kind of yellowish cast to the lighting. Okay. Now, an important thing here is that it's a nice smooth curve, but it's very weighted towards the red part of the spectrum. Here's another kind of lighting that we've had for years, cool white fluorescent. Now, the way that fluorescent lamps work is it tends to be very spiky energy at each of these different levels. So you see here the red area is very low, and we've got some very pronounced peaks in the greens and yellows and off in the blue section. And it's not very uniform at all. It's very intense in some areas, certain wavelengths of light, and it's very weak in others. What that'll do is with certain colors that you print, when you reflect this light off of it, some colors in the ranges here where we've got a lot of light energy, they'll be amplified. Other colors, like say reds, when this light hits it, they'll look duller because there's very little light in that energy. And then here's yet another one, a TL84, and you can see here very pronounced spikes in the green and the yellow, and across the rest of the spectrum, it's much lower. Again, any colors that are very low here, because of that low energy in that light source of those wavelengths, the products will have very reduced or dull looking colors in those areas. Whereas if it's in the right wavelengths of yellow and green there, they're going to be really amplified or strong looking under this light source. So as I mentioned, D50 is our industry standard. To view that properly, you should have a viewing booth that aligns with an ISO standard called 3664. And this describes exactly what the light should look like, okay? Exactly what D50 needs to be in there. In fact, it even includes a certain amount of ultraviolet light that needs to be included in that light source. This aligns with our instruments that when we set these instruments to the newer setting called M1, it aligns very well with this lighting illuminant, okay? It's really important to have a viewing booth like this available when doing critical human viewing of the printed piece as opposed to taking measurements. Measurements are very important, and visual validation is also important. So you need to have really good viewing to do that. Some of your viewing booths will also include not just the D50, but they'll have the option to switch it over to a fluorescent, like a cool white fluorescent or that TL84 that I showed you. And some will also include the ability to flip over to show it under incandescent lighting. Others will also have options to turn on a UV lamp so you can evaluate the impact of the optical brighteners on your papers and even in some of your inks. Here's an example of some samples that were viewed in a viewing booth, and you can see how distinctly different they are. So at the top, that's D50. Again, that's daylight. Okay, so that's what your product's going to look like under daylight. And down below, you'll see what your product would look like under, say, incandescent or cool white fluorescent. Now, we do all of our measurements based on this same D50 you see at the top, but for a lot of customers, they also want to know, what's it going to look like under these other conditions, especially when I'm comparing print that's made with different kinds of technologies, and I want to make sure they still match under these different conditions. And we'll talk about that more later. There's also, in a number of papers that we work with, there are optical brightening agents, or OBAs, that are added to make the paper brighter. And these, they have their own challenges, especially the fact that they, some of them will burn off after a time. So they look nice and bright when the paper on the box is new, but if there's a lot of OBAs that burn off, if it sits on the shelf for a long time, they may dull. So the viewing booths do have the ability, some of them, to view the UV impact on that substrate. So on the left side here, we've got a paper, a box printed with with OBAs included, and on the right there's no OBAs. And when we flip on the UV light, we see the glowing of those optical brighteners. So that's an option that's in some viewing booths to evaluate how much of this do we have. So that's about the light. Let's talk about the object. So the light, which has all the color in it to start with, reflects off of an object. The object absorbs some of the colors and then reflects others. Okay, in this case, this is going to absorb most of the wavelengths of light except for red, and then red is reflected. Okay, so we've got that color would equal a certain spectral reflectance curve. In other words, much of the light is absorbed, as you can see here in this curve. Everything from, say, the blues and the greens it's mostly absorbed. Very little is reflected. And then on the right, the reds, the oranges and yellows, those are reflected, and that's what provides us with that color. Okay. Here's some examples of other kinds of curves. So if you look here, you'll see the red curve on the right side. The wavelengths of light that have a lot of energy reflected off of them are ramped up on the right side. If you're looking at a green color, that'll look like that curve there with the green that shows that most of the wavelengths in the middle will be reflected a lot, whereas the others are all suppressed. And then blue would be, again, peaked over on the left side of the graph here, showing those wavelengths are, emitting a lot of energy. If we're looking at a color that's fairly neutral, like a gray, we would see, like you see there, a gray, fairly uniform across all wavelengths of color. That would provide a gray. If it's got very little reflectance, of course, that's going to be very little energy. That would be black. And of course, white is the top. Now, you see that dotted line there. You may be wondering, why does that go way above 100 on the left side? What that is that's the UV bump. So with optical brighteners on a white paper stock, what it does is it absorbs light in outside of the visual spectrum and reflects it amplified on the left side there, which makes that box that I showed you earlier appear brighter. Okay, but in fact it's bluer, but our eye doesn't sense that. It just sees it as a brighter color, a brighter white. Okay, so that if you see that kind of measurement of your papers, that wouldn't imply you've got some optical brighteners going on. Now the human eye.
And Mark, just a question or two, please. You mentioned about the actual light booths a moment ago. Is there an actual lux or light intensity value that there should be in the light booth?
Yes, and I apologize, I don't have that off the top of my head, but ISO 3664 actually does describe different different levels of intensity for the light for different types of viewing. That's a really good question. There is a certain level that's described in there for like casual comparison of colors. And then for critical comparison of colors, that value is higher. And I apologize, I don't have the number off the top of my head, but it is specified in 3664. And your viewing booths, most of them, the modern ones, will comply with the critical viewing intensity levels.
Okay, great. But then the viewing booth should either be D50 and D65 or D50 only? Oh,
good question. So D65 is typically not used in the print industry. It's used in other industries such as paints, plastics, textiles. But in print, it's typically D50.
Okay.
Okay.
Thanks a lot.
Yeah, great questions. Okay, so the human eye has basically two types of light sensors, receptors, okay? The rods are used to sense the level of light. They don't really measure color. And the cones are actually our receptors that measure color or see color. So the cones, there's one that's a group of cones that are sensitive to the red parts of the spectrum that we looked at. There's a set of cones that are sensitive to the green part of the spectrum. And as you'd guess, there's another set of cones that are sensitive to the blue part of the spectrum. In fact, the question just asked is relevant here because the cones work differently under different intensities of light. You need to have a lot of light for the cones to work well. And so that's why our viewing booths have that requirement of a certain level of intensity to be able to critically judge color. Now, when you have lower levels of intensity, the cones don't work as well. In fact, when you at night, when you're walking around, you've got much lower lighting, the cones don't work at all very well, and it's the rods that we're seeing with. So you may think about, like, when you're out at night, you don't see colors very well, but you can still see to get around. That's because the rods are helping us be able to see under those lighting conditions. But the cones they require intense lighting to be able to judge color very well. So the question was perfectly timed. So the human vision across the spectrum, they've mapped this out, and they've figured out the sensitivity to wavelengths of light by those different cones. Okay, and they plotted those out. So across the spectrum, this is the human response curve, how sensitive we are to different wavelengths with each of these different cones. And you can see it covers the whole spectrum, but each of those cones cover a part of it. And there's a bit of overlap between them. Now, here's a little test you all have to take yourself. This is a test that's done to help determine the sensitivity that people would have with their cones, how well those cones are working. So what you should see here is a number kind of mixed up in these dots on each of these. The one on the left is a single digit, and the one on the right is 2 digits. And what you should be seeing here is 6 and 45. Now, so some of you may be a little challenging, but if you look closely, if your cones are working properly, you should be able to kind of decipher that in there. The way these work is that you've got red dots and green dots here, okay? And for someone that has what they call red-green deficiency, they wouldn't see a difference between those. They'd all look the same. Now, for those of you that have cones working properly, then you would be able to decipher the difference between those two. This is what it would look like if you had a red-green deficiency. In fact, here's just some other examples. On the left side, you'll see this kind of rainbow of colors there. And if you go across, these are other common green, red, and blue deficiencies, and a fairly rare true colorblind condition on the right, where all colors look the same. They just have different lightnesses to them. But you can see where people have issues where certain cones are either weak or not working. It really impacts how they interpret colors. And this is actually also important for product design, shelf design, for displays, to make sure that people can actually read the displays or see the designs you intend. So there's actually people that design products to make sure that they're visible to all people with different viewing conditions or different viewing abilities. All right, let's roll into the numbers of color. We're going to quantify these colors, okay? So for starters, let's talk a little bit about how a spectrophotometer works. The sample is across the bottom here. With the typical instruments we use mostly in our industry, like the Exact and the Exact 2, these are what we call a 45-0 spectrophotometer. What that means is the light is projected at 45-degree angles to the sample, and then the 0 degree straight up is the reflectance that goes into the receiver or the sensor on the instrument. Okay, on its way, it goes through a filter wheel, and it has these filters evenly distributed across the visible spectrum, and we capture samples of the light under each of these different filters so that we can plot out a graph similar to what I was showing you earlier with the spectral reflectance curves. So we start out with a color sample. We measure it. We gather spectral reflectance values across all of those different wavelengths. And we can plot a curve that represents the color that we just measured. This spectral data, this is the DNA of that color. It's exactly how that color exists, okay, and it includes everything about it that we need to know. Now, for a lot of our stuff, though, we can't work easily with spectral reflectance curves. It's a little easier or intuitive to work with a smaller number, a set of numbers here, okay? So what we do is we take the light source. Now, the light source, remember, it has a certain amount of energy in the light across the spectrum. It reflects off of an object. The object absorbs some of the light and reflects other light, okay? But remember, it only works with the light that's on it. So if the light happens to be very red, it's going to impact that. And then the observer, based on the sensitivity of the cones, observes certain levels of energy, okay, across these different cones. And this is what we call our XYZ. And we can take that and then mathematically convert that out to numbers that we use commonly in our industry, most commonly LAB and sometimes LCH, okay? Now, what do those numbers mean? We use them a lot. We see them, as specifications and such. But let's talk about how they work. They both, LCH and LAB, are describing the same color space in just different ways. So it's kind of like longitude, latitude, and altitude would tell you exactly where you are on the planet Earth. With 3 of these numbers, we can tell you where you exist or what you're looking at as far as a color value in the color space. So L, that's the easiest one. That's the lightness. That's the axis right up the middle. So how light or dark is that? Okay. So a very dark color is going to have a lightness or an L star of 0. And the theoretical maximum is going to be L star of 100. So that's our lightness. With the most intuitive model for, actually was used somewhat in designers in the past and stuff, is looking at chroma and hue next. So the C and H, chroma describes how vivid or saturated that color or how dull it is. And hue is just going around the color wheel and looking at the hue angle around the color wheel. Most of us use in the press room, and for most of our tolerancing, we're going to use LAB. And here, the A represents a range from negative colors of A would be green, and the positive numbers for A would be on the red side. So if you're going positive, you're going reddish. If you're going negative, you're going greenish. And similarly for the B, going negative on the B is going bluish and positive is yellowish. Okay, and here, when you get to something where the A and B are 0, 0, that's truly neutral. And of course, any numbers that are near 0 are fairly neutral, okay? So common for like your paper stocks and such. All right, so if we're looking at a color that's say 47, 68, 48, well, that's kind of like that red ball we were just looking at, okay? That's off. We're going up that L value up to around mid-range there at 47, okay? And then we're going to go in the A direction off to the right, okay, about 2/3 of the way across, okay? And then we're going to go in the B direction, moving towards the red sector there, okay? Here's another LAB. This one's 25, 1, -2. So that one I'm going to be down towards the low end. Okay, so I'm coming from the bottom, go up about 1/4 of the way up. And it's -1 and 2, so it's fairly neutral. So that's going to be a darkish gray, right? And then here, another one, again, kind of about half. Oh, I put the wrong number in there. I originally put a different number in there. I must have made a mistake on this slide. But you get the idea. These describe how we navigate through our color space to find a specific color. Is it in the green area? Is it in the bluish area? That kind of thing. Okay. Oh, actually, no, I'm sorry. This one is my mistake. This one's in the -68 direction. So on the A, I'd be going off in the green direction first. Okay. And then moving towards A as a 48. And so that would kind of be a grass green, actually. Okay. What is delta E? That's really important to us because we use that for a tolerancing method a lot. Delta E, by its simplest thing, is we're going to start out with a standard, and we're going to look at how far in any direction are we allowing our color to vary. So that would be our tolerance, okay? Delta E is a difference in color, and how much are we going to allow is our tolerance. So there's different tolerancing methods. There's an unweighted method, okay, which means equal in all directions, okay? This would be our traditional just delta E, or sometimes you'll see it as delta EAB or delta E76. This was used for a lot of years in our press room, especially for your CMYK tolerancing, ISO specified to use delta E and so on, okay? It means you pick your point in any direction, an equal amount, okay? So it's a unweighted or uniform direction. However, it doesn't correlate real well with how we perceive color differences. We do perceive colors in kind of an ununiform way. We're a little more sensitive to changes in the color or hue angle, okay, of the color than we are sensitive to, say, the saturation or the lightness of that color. So consequently, we create this like ellipsoid shape around that target color, and that becomes our tolerance. We use something called Delta E CMC for many years, okay, especially in the ink rooms for this and the spot inks, okay. But more recently, in the last 15 years or so, we've been really using more and more of Delta E 2000, and that became part of some of our ISO print standards and a lot of our brand requirements, including for CMYK inks. So if you looked at these tolerancing areas around each of our standards, what you would see if you looked at different colors is it's weighted depending on the location in the color space. So again, hue is prioritized over the chroma and lightness, and in the duller colors, those towards the center of the color space, they're going to be smaller ellipses, okay? And then as we move out to the more saturated areas, we're going to see much larger ellipsoids around these, okay? So it's allowing for a much larger difference in color measurement before we'd see a perceived difference in color.
Mark,
Yes.
just a question for you. Is there any advantage of using the spectral data over LAB?
Absolutely. Yeah. And we're going to cover that towards the end of this slide deck. But no, that's critical. That is very important. Now, in what we're talking about here for tolerancing, though, that's a good point there, is it's kind of hard to tolerance on a spectral curve. But this is where using LAB is a little easier because you can tolerance based on those three numbers and how much you're moving in the color space. But the spectral data is going to be critical for ink formulation and a number of other things that we'll look at in a moment. So the weighting factor on these, or it describes how it's going to, the shape of these ellipsoids. We used for CMC 2-to-1 for years. I don't want to spend a lot of time on CMC because it's kind of old school, but I just kind of want to reference it. There was, they actually did put a 2-to-1 in there commonly instead of just using the 1-to-1 on those. And the reason I mention that is because some people get a little confused because when they get to Delta 2000, they think they need to plug that 2 in there. But actually, Delta 2000 was built with a weighting factor that you want to leave at 1-1-1 because it's already optimized to match human perception pretty well. And so you don't want to change those weighting factors. So in some software, if you see the ability to change those numbers, don't change it unless you've got a really good reason to. The default, the industry standard is always going to be 1-1-1. So we just talked about 3 different methods. Which one should I use? Okay. You're going to see all these things all over the place. Well, what's critical is you need to always communicate both the tolerancing method and the weighting factor, okay? And again, that green one up in the upper right corner there, the Delta 2000 1-1-1 is going to be the one most commonly used right now, okay? So that's the one you want to probably go with unless someone defines some other method to use. And generally, if they're defining another method, it's actually probably something that's not been updated for a long time, because most of the brands and definitely ISO have moved on to Delta 2000 for most of their tolerancing many years ago. Whatever you do, though, make sure everybody's communicating using the same method and weighting factor. So if a customer does require that you use Delta E CMC, if that's what they require, make sure you're measuring in that method and reporting in that method. But you may want to have a discussion with them and see if they actually mean that to use that. And then the other question comes up is, well, how much tolerance should I put on my colors? You know, is it 1 Delta E? Is it 5 Delta E? How much of a range should I allow? Okay. Well, that's an agreement between the print buyer and the print supplier, but it really should be based on the print capability. Some of your presses are capable of holding tighter tolerances while others are not. For example, if you're printing on a corrugated board stock on a brown craft paper, the materials that go into making the substrate itself vary significantly, and it's going to introduce more variability in the process. But if I'm printing on a white film and it's fairly consistent, then I can hold maybe tighter tolerances. Okay, you have to look at your actual print process. So some people actually go through the process of doing a statistical assessment on their process to see how much variation do we have in our print production, and use that as a guidance to determine what tolerance they can actually expect out of that type of production. Now, commonly, the offset print tolerances, for example, to match a print standard. Okay, in fact, this applies across other print flexo and gravure as well. But commonly for your CMY inks, they'll be somewhere around 3.5 Delta E. The K might be up to 5, and spot inks are typically held to somewhere around 2, maybe 2.5. Okay, but again, always considering the variability within that print process. There are some other tolerances that you'll run into out there for print production that I just want you to kind of be aware of. For those that are printing, that are looking at G7, that's primarily G7 printers, they'll often look at the weighted Delta L and the weighted Delta CH of their gray balance patches. So the weighted L is looking at the difference in lightness of a color without the regard to the color. It's just the lightness. And the weighted Delta CH is looking at the difference in color without regard to the lightness. So it's just looking at how much is the color moving, but don't consider the lightness change. But those are kind of specialized for, again, G7 folks. And then there's another one that's commonly used in flexographic printing, and that is looking at the Delta H, okay? So that's looking at just how much is the hue angle change. And this is because there's a wide variety of printing materials that we're working with in Flexo for packaging. And one of the primary things is matching that hue angle, and then adjusting the press to get the best color saturation of that ink while still maintaining the hue angle. So in some cases, they may specify that as well. Okay, but moving more towards the looking at the full Delta E, but that does exist. All right, so back to that question about the spectral data. So spectral data is really critical for color specification and ink formulation. For those of you that have Pantone books, and I imagine many of you do have access to them, if you look in the back of the formula guide, and if it's a fairly current one, you'll see what's called a lighting indicator. And I've got that example here, pictured here. There's two different colors there, actually. And if you're under good D50 lighting, the top half and bottom half of that color field will match pretty close, as you see in this illustration here underneath the little sun icon there. They match pretty well. But in fact, they have the same LAB value, but the spectral curves are a bit different because we used a little bit different pigments in these colors. And so what happens is, if we put it under, say, fluorescent lighting, then you'll see a difference in these colors. And this is what we call a metameric pair, okay? Now, where this is really critical is, imagine that you're printing a product, maybe you're printing the box that a bottle will slide into, okay? If you just go off of LAB values, you'll get a spectral result in your ink that you create, but you don't know what that is. It's not defined as to what it should be. And then somebody else makes the label that goes on a bottle that's going to go into that box, and they go with just the same LAB, but they use very different pigments that end up with very different spectral curves. Okay. And what they can end up with is a result we see here. The label that goes on the bottle ends up looking different than the box when it's under store lighting. But when you take it out in daylight, suddenly they match. This can be a really critical thing when you've got a variety of products that are printed in different ways that show up on the store shelf that are adjacent to each other, and they're not matched spectrally. They will look different on the shelf, and the brand owner is not going to be very happy with that. Okay, so let's take a look at how that works. So with that patch in your book, if you've got your spectrophotometer, you can actually measure this and see how this works. So I've got my patch. I've measured the top half of that indicator here, and I made that as a standard. And then I measured the bottom half, and that's my my sample. And you can see here the target and the sample under D50, they match pretty well. They're under 1 delta E. And if I look at my LEB plot over here, it's showing me it's a pretty good match. I could sell that all day, right? If just LAB was, if it's all mattered, that's all good, right? But in the software in ColorCert, we can flip over the illumination here to F11 to say, what's this going to look like under fluorescent lighting? Same measurement data, okay? Just change the illuminant here. Now I see that it's going to be, almost 8 delta E. You can see it in the graph here. You can see it in the example in the middle here, the target versus the sample, very different. So why is that? Well, the spectral curves kind of trend the similar way, but they cross over each other several times. When you start to see this kind of effect here, where it's crossing over, like in this case, 5 times, that's going to be a good indicator. You're probably going to have the color flop under different lighting conditions. So again, imagine the products on the shelf made that they don't match in spectrally. Under different store lighting, they're going to look different. Okay. So what's critical here, the press operator can't change the spectral curve. They can only work with the ink that they're given. The ink technicians need to work with the spectral data to try to match the pigments they're working with to the spectral curve of the standard. Pantone colors, Pantone Live colors are all specified spectrally. When the ink technician would pull that into their formulation software, they would actually match that. And we're going to talk about that in our next session, actually, a little bit more. But they would actually match their inks more closely to the spectral curve. And when they match the spectral curve, they'll also match the LAB. Because remember, the spectral curve is like the DNA of that color. And you can have an LAB value can have several spectral curves. We've got 2 spectral curves right here that end up with the same essential LAB. Okay. You want to make sure the ink technicians are working with the spectral data. You never want to just type in LAB data into ink formulation software, because you don't know what spectral curve it's going to come up with to get that match. Always work with the spectral data. Alrighty, and again, we'll talk more about that ink formulation in our next section. So what
Mark, sorry to ask, another question for you. You referenced earlier about the light indicator on the back of the Pantone books.
Yes.
Do these work well under LED lighting as well? Because, there's a commenter to actually sort of say maybe they don't. Is that a reason? Is there a reason why that is the case?
Well, I haven't looked at that specifically. It would have everything to do with what spectral energy is in that LED lighting, and I have not looked at how well the LED viewing booths are performing to match the D50 standards, but the different that actually brings up a question about the quality of the viewing booths, for that matter. There are more expensive viewing booths out there that match the spectral energy of D50 more closely. The less expensive ones are going to use fluorescent lamps, that the spectral curve is not a perfect match to the D50 standard, but they're within tolerance of it. So you still may see a slight differentiation between those two patches under that condition. And the LEDs, if they are tuned properly and if they are putting out the right amount of energy at each of the wavelengths, it should behave the same way. But I haven't seen it firsthand, so I don't know what's going on there. But if the spectral energy in the LED light source doesn't match the D50 standard well, then the color difference will be more evident in those patches.
Okay, great, thanks. And one last one is a case of that. Could you expand a bit more, please, on what you mean by when it says weighted delta E?
So when I was talking about the weighted delta L and weighted delta CH, yeah, good question there. So actually, so within the G7 requirements, what they're looking at is actually most of the time they're looking at multiple gray balance patches or multiple black tint patches to validate compliance to G7. So a very common scenario is looking at a 25, 50, and 75 tint value of black and a 25, 50, 75 builds of CMY, neutrally balanced builds, and looking at how neutral the weighted average of those patches are. Okay. So that's where the weighted part comes in. So I apologize for not being clear on that earlier, but yeah, it's looking at oftentimes more than just one patch, looking at maybe 3 patches or more and averaging those.
Okay, no problem. And in respect of the LAB, why is it that we can actually have 2 colors with the same LAB values but result in different shades?
Oh, okay. Well, okay, good question. So it's, remember the light object observer, right? So the light is the starting point of the color. So the amount of color across each of those wavelengths is different for each of these. So when I put in this example on the screen, let's go back here. When I shine daylight onto an object that has these spectral reflectance curves, the amount of light that's in this source reflecting off that object, the light is fairly uniform, let's say, okay? And so these, since they trend pretty similarly here, they end up looking pretty similar here. Now, if I change my light source to one that has a lot more spikes in it, a lot more intensity in different parts of the spectrum than daylight does, it's going to amplify different parts of the spectrum in different ways than daylight did. And so in this case, it amplified a lot of the stuff over here in the red here, making this look more red. Okay, so based on the fact that that light source has a certain amount of color in certain areas, it will have that kind of difference in the reflectance on those, because we use different pigments to build out those curves. But again, under D50, they behave similarly, but under other lighting, the lighting is the important part there. It's the other lighting that changed how the color looks.
Okay, thank you.
Mm-hmm. Excellent questions. All righty. So today, what did we learn? First of all, human perception of color can be deceived. It's inconsistent. And I alluded to instruments are more repeatable. Okay. Density is not going to tell us if we have a color match. It is a good color metric. You can use it to control, the ink film thickness on a press, for example. I'm going to put more ink or less ink. You can use that as a control metric, but it doesn't tell you if you got a color match. Okay, so you still have to look at color to see, do we have a match? And LAB and delta E give us a great way to quantify which direction is that. Okay, is it off color or is it just off in density? That kind of thing. Color is the product, and this actually comes right back to that last question asked. It's the product of the light as well as the object and the observer. Okay. So if the light changes, it will change how the object reflects the light. LABCH is, again, as I mentioned a moment ago, it's a great way to describe color and the direction of the difference. Okay, it's a lot better than just density, which tells you how light or dark it is. Delta E methods describe the size of the difference in colors, and your production tolerances need to be based on your print process variables. And lastly, spectral specification is critical for ink formulation to reduce product mismatch on the store shelf. All right. So for next time, I'm open up. Are there any other questions that we've got here before
I can see some coming in. Thanks, Mark. So you mentioned about you've clearly articulated LAB. Thank you for that. But you also referenced XYZ. What are these representing at all? Is it a case of they coordinates, or what's the XYZ?
Yeah, so that's actually tied to, if you recall the curves I showed you that represent the sensitivity of the human eye to different wavelengths of light. So, the red cones, the green cones, and the blue cones. The XYZ are looking at numbers derived from the amount of feedback we get from the red cone, the blue cone, and the green cone, mathematically synthesized. It's not something we use in any of our tolerancing software. It's typically used for the math under the hood of the software. So oftentimes, end users won't see that, okay? Kind of like actually in a lot of our software, we use a spectral information under the hood as well, and you may not even see it there, but it's used for a lot of calculations that are done, okay? But yeah, the XYZ specifically is about the human perception of that color in each of those wavelengths.
Excellent. And here is a question about the actual different ink film thicknesses. If you actually have significant film weights in there, can you still actually technically have the same color match?
So if I understand correctly, yeah, as I change the ink film thickness, the density will go up, and of course the LAB will change. Okay. In some inks, it moves more than others. So if I'm like measuring black, for example, the density will change more rapidly as I change the ink film thickness. But if I'm laying down more yellow, that density will change slower as I increase the ink film thickness. But they do change together. As I increase the ink film thickness, the density does go up. But the key is, and we'll see more of this in our next section, actually, to control that press, in order to match the LAB, you adjust your ink film thickness up or down, and your LAB will move, and you're going to try to find the optimal density or ink film thickness to achieve the closest match in LAB. And we've got tools to help you do that.
Excellent. And is there in terms of density, is there a danger in actually just giving out density values? Because maybe if you're in North America, you can actually have a particular value, in Europe have another value. Is that?
Well, actually, there is something to that to some extent. There is a danger anywhere you just do density, but in Europe they use status E typically, and in North America it's status T. Now that's just a setting within your instrument to determine how it's going to report back the values, the scale it's used, and so on. And so those and that impacts mostly yellow, in fact. So yeah, if I were targeting a yellow density and I just gave you a number of density and you were printing in a different region, you might misapply that. But actually more fundamental even than that, and that is a critical issue, but more fundamental than that is yellow seems to be the biggest problem with density, actually, because the example I showed you earlier was with yellow, and I picked yellow because I run into that so often on so many presses, particularly offset litho, but many presses. When the yellow is running, oftentimes in certain types of presses, it'll pick up contaminants, and it'll dirty up the color, and the density measurements will increase. But in fact, it's just dirty yellow ink. It's not denser. It's not more ink. It's dirtier. And if the press operator continues to run just the density, their color starts to drift off, but they're hitting the numbers and they think they can keep hitting them all day, when in fact the actual visual appearance is changing.
That's a very good example. And in terms of measuring, as you say, starting to actually get into the numbers now, I mean, is there any difference, if you like, to actually sort of saying, is one better than the other, to actually say, I'm measuring in LAB, or I'm measuring LCH, or even if I combine the two, LABCH, is there a preference or guidance that you could give people?
Gotcha. Okay. So, I'd say most of the industry is using LAB. There is a smaller group that's using LCH. And as you alluded to, there are some people that have LABCH all enabled within their software to show all those numbers. And actually, it kind of boils down to really what communicates color well to your operators. So and across your supply chain as well. So you're usually going to find LAB is the most common way to communicate the color and color differences kind of thing. But if I'm looking at my software and I see a delta L, okay, that tells me, like I said earlier, it tells me what's the difference in lightness. If I see a delta A and the delta A is a negative, that tells me the direction that my color is moving, okay? It's moving off in the green direction. And if I look at the delta C, well, is it more or less chromatic? And sometimes that can be a clue. If it's getting less chromatic, for example, that means my ink's getting duller. That might be a clue that it's getting dirtier. So there's certain things you can learn just by looking at the direction of the color movement, and then looking at what your process is and what could contribute to that. If you're looking at overprints of red, green, and blue, which are combinations of two inks, if you look at the direction in A or B, it might give a clue as to which ink is trapping more relative to the other ink. And you have an ink trapping issue because it moved, more towards the bluish or cyan direction as opposed to the yellow direction to create my green. So how well can your operators look at these numbers and use the directionality to analyze their problems?
That's a good answer. And respect of, varnishes are sometimes used as well. Is there any advantages of actually using maybe what the impact of a varnish has? Like if I actually use, if they measure with, let's say, LAB, is that better with a varnish, or is it still the same point?
I think it's still pretty much the same. And yeah, you will see, if you're comparing your print result before and after varnish, for example, you may see that, this varnish is moving things in a more blue direction or more yellow direction. And, how big a move is it? And is that going to be acceptable? The other thing that is important, since you bring up the varnish, is that most of your customers care about what some people will call shelf color. What does the final product look like when it's sitting on the shelf? And that would include whatever varnish or final treatments, laminates, or whatever you're applying at the end of your process. So measuring colors prior to varnish or lamination may be a little different than your end result. So you do need to consider the final result. So if you're doing your final QC of products, it really probably should be with the final varnish or laminate applied to make sure you're actually hitting the customer's target color that they expect on shelf.
So you would actually recommend, if it's feasible or possible, to actually best practice to actually capture a kind of a before and after, right?
Yes. Yeah. Because that way you can provide a target value during production prior to lamination or varnish. If that, in some cases, is in line, so you're going to capture it at the very end. Varnish is often done right in line, right? Lamination often is done offline. So if you're doing, an offline final treatment to it, you may need to capture a process, in process value. When I pulled off my press, it should measure this value, and I expect it to match with varnish or the laminate at another value. So,
yeah, because I mean, somebody could walk in with a sample, right, of actually a finished sample and say, I want you to match that.
that's right. And if you measure it pulling off the press before you've laminated, you're looking at a different state, right?
Yeah, yeah. I think we're actually out of time, but I mean, there's going to be more questions coming in. But as I said before, please do keep the questions coming in. We'll do our best to answer them over the next days or so. But Mark, you were actually then going to touch on to the next sessions. Yeah.
Yeah. So definitely, I hope you all come back to join us next time. We're going to talk a little bit about, using digital standards versus physical standards. We're going to look at digital color standards and how they're specified. We're going to look at spot color dependent standards for various print conditions, how to manage spot color standards throughout your supply chain, industry standards for process CMYK, in fact, CMYK orange, green, violet, and how they apply to different press conditions, and then validating your production with intuitive and actionable feedback. So that's what we're going to cover next time. And then we'll have a third event after that.
Thank you, Mark, for actually doing everything that you've done today. As I said, please keep the questions coming in. Just to repeat myself, the actual everything will be shared with you. You should actually get links following this to actually the recording, and thereafter you'll actually then start to actually get invitations for the next sessions where you can actually, again, like today, start to actually log in, register, and follow up from there. Again, Mark, great session. Thank you for your time. And hopefully we'll speak to you all soon.
Take care.
Thank you.